We are continuing our investigation of scientific reasoning by looking at the hypothetico-deductive method a little more carefully. And in this video, we'll talk about incremental confirmation and disconfirmation. And incremental confirmation is the way that we progress in science. We don't just suddenly have breakthroughs that are immediate and clear-cut. Most experiments confirm a hypothesis in an incremental sense only. So it's only to certain degrees that we are more confident after the experiment than we were before the experiment. So confirmation here, when we're talking about confirmation, again, it's not an absolute term. It means that the probability that the hypothesis is true is greater after the test than it was prior to the test. We've increased the likelihood that we are on the right track when we have conducted an experiment that confirms the hypothesis. It's an incremental confirmation. So an hypothesis is confirmed in an absolute sense only when there is a tremendous amount of evidence for the hypothesis. It's been repeated by several people in a variety of settings, and there are no strong cases that count against the hypothesis. There's no strong evidence against it. So, for example, the Copernican theory of the Earth and the Sun, that for a time, it was for a long time, Ptolemy's theory was the one that held the idea that the Earth was the center of things and the Sun revolved around the Earth. And it took a while with Galileo and Copernicus to provide evidence that it is actually the Earth that revolves around the Sun, along with other planets. And initially that was confirmed in increments, but of course, through the centuries, we don't have any strong evidence against it. We're really confident the Copernican theory is true, that the Earth really does revolve around the Sun. So we can just say that that's true, that the Earth revolves around the Sun. At this point, it's been confirmed in a more absolute sense. So let's continue to think about this. Even if an hypothesis is absolutely confirmed, there's still this possibility. It could later be disconfirmed. That possibility always remains, even when we're extremely confident about something. So just a couple examples, Newtonian laws of motion for several centuries were confirmed, and it just seemed like an absolute confirmation. The addition of velocities, for example, worked. Everything made sense. It all worked until the 20th century. We started to realize that it's false at velocities near the speed of light. And so even though it was absolutely confirmed over several decades and even a few centuries, we later found out that there are cases that show that it's not an absolute truth. Another example is the biological claim that all mammals bear live young. So for several decades, and probably more than a century, that was believed to be true, and all the mammals that scientists investigated, of course, bore live young, and so there were no exceptions to that rule until we explored further past the Americas and got to Australia and New Zealand, where we found some monotremes that are mammals, such as the platypus and echidnas. And they are, in fact, mammals, but they lay eggs. And so even though that was confirmed in a more absolute sense, we did find some evidence later on that disconfirmed it. Now, the more unlikely the prediction is to be true, unless the hypothesis is true, the greater the strength of the confirmation. So this is just a way of evaluating a particular test. To what degree does it confirm the hypothesis? Well, we have this standard, right? The less likely the prediction is to be true, Unless the hypothesis is true, then the greater the strength of the confirmation. That's exactly what you want. You want a prediction that's very unlikely unless you're on the right track. And then if you can do your experiment and confirm that the prediction is in fact true, then you've really made some ground. So that's how we evaluate incremental confirmation. Now, let me talk a little bit about pseudosciences. Pseudosciences such as astrology violate the rule we just mentioned. They make claims or predictions that are very likely to be true, whether or not the hypothesis is true. And thus, even if the prediction comes true, there's very little reason to think the hypothesis is true. So the hypothesis might be astrology is correct, or horoscopes are correct, or this person is a psychic because they told you that you will have a change at work or home. And wow, suddenly, within the month, you had a change at work or home because somebody got sick, or your boss implemented a new policy, or you got fired, or you got a promotion, or any number of things would fit into that prediction, so-called prediction. So it's very likely to be true, and it doesn't give you reason to think the psychic is correct, actually a psychic, that these things work. Another example, if you're in Logic 140, my course, the textbook there that we use from Marilee Salmon, is she gives the example of a quack health remedy where somebody has a common cold and they hear of a physician who can cure the common cold. And the technique is you remove your shoes and socks, and then the physician shines some infrared light on your feet, and then you have to come back for several more treatments. But after several days, it cures your cold. Well, the problem, of course, there is that after several days, you're very likely to have recovered from the cold anyway. So you really don't have evidence that it was the infrared light that was doing. Just one more example here, and this is not quite as clear-cut example as the two I just described, but fad diets. Fad diets can work if you restrict a diet to one particular type of food or an extremely limited type of food, say even if it's ice cream. So you could go on the ice cream diet. I've never heard of anyone doing this, but you could try it. You go on an ice cream diet, you eat it for breakfast, lunch, and dinner, you lose weight by doing that. Okay, now why is that? Because you get tired of ice cream. I know it's hard to believe, but it would be true. Eventually, you just don't eat as much. You decrease your caloric intake substantially, and then you're going to lose weight. Of course, the problem with these kinds of diets is that you cannot stay on them. You know, eventually you want some pizza or even some bread or something else besides ice cream. And so you go off the diet. So it could work for a while, but it's not the kind of thing that you could stay on forever. And of course, you would bounce back and gain all the weight lost. Typically, that would happen. Okay, let's talk about disconfirmation. We've talked about incremental confirmation and absolute confirmation. How do we disconfirm an hypothesis? Well, the method of reasoning goes like this. Suppose you do have an hypothesis that is initially plausible. That is, it has some degree of prior probability. It's not a zero probability, and it makes sense. And then you have this kind of reasoning. If the hypothesis is true and the auxiliary hypotheses, and here there would be several. So, for example, if you were Copernicus trying to confirm his view that the Earth revolved around the sun, part of that involved observations of Venus with a telescope. Well, you had to assume the telescope was functioning correctly. And if you invoked you made use of a grad student, you had to be confident the grad student was reporting things correctly and wasn't just sleeping on the job, et cetera, et cetera. You have all kinds of auxiliary hypotheses. So if both the initial hypothesis and all of those are true, then the observable prediction is true. And then you make the observation, and the observable prediction is false. If that turns out to be the case, then you have reason to think that the original hypothesis is false. That's disconfirmation. Now, if we just look at 2 and 3 leading to 4, you might say that this is part a deductively valid argument. Now, it's not. Part of that, and the main reason for that, I guess, is that the hypothesis, and we're assuming auxiliary hypotheses, but we're only concluding that the original hypothesis is false. There could have been a problem with one of the auxiliary hypotheses. And so this is actually inductive reasoning that we are using in disconfirming an hypothesis. Okay, finally, a word about crucial tests. Crucial tests are rare. They occur when an observable prediction confirms one of only 2 competing hypotheses. And at the same time, it disconfirms the other. So you have 2 competing hypotheses. One of them says this prediction is going to be true. The other one actually says the contrary to that, or the contradiction of that, that the prediction is going to be false. And so that is a great test if you can find one. Now, an example, and this is a little bit stretched, but the idea when Jenner was trying to develop a vaccine, a way to protect people from smallpox, he was using cowpox, and he would inoculate people with cowpox and then see if they were immune to smallpox. So his thesis was, his hypothesis being tested was cowpox confers an immunity to smallpox. Now, in contrast, of course, we would have cowpox does not confer an immunity to smallpox. So he does this, he inoculates some children and some dairymaids and, vulnerable people here with human trials. And anyway, he finds out that it is correct. So Jenner's tests are close. He did find out, he confirmed that cowpox confers an immunity to smallpox, at least to some degree. But these kinds of crucial tests are rare. Usually there are at least a few plausible alternative hypotheses that might remain, some other kinds of explanations of the prediction that you got. And so maybe there was something going on with a common background with the people being inoculated so that they were already immune to smallpox in the case that we are talking about. Possible, right? Okay, so that's how scientific reasoning progresses, some of the limitations, some of the problems with people claiming to be doing science, the pseudosciences. In the next video, we're going to look at a very important tool to use, and that is Bayes' theorem.